We're doing some resistor practice problems today. To do these problems, you need to know about Ohm's law, the basic rules for adding resistors in series and in parallel, as well as the concept of Thevenin resistance. I won't be doing any problems which require the use explicitly of Kirchhoff's voltage or current laws or other more advanced resistor network techniques. We're going to start with a series of problems in which we're going to solve for the dissipated power in each circuit component, and that's going to require knowledge of the voltage and current in each component as well, and then do the same for the entire circuit. Finally, we'll identify which resistor in each circuit dissipates the most power as well as the least power. This could be easy here in our first problem because we only have two resistors. It's a 12K and a 2 mega ohm resistor in series with a 18 volt power supply. So we're going to begin by turning this problem into a single equivalent resistor. So here's our equivalent from 18 volts to 0 volts. With that equivalent resistor is the sum of these two. I'm going to go and label my resistors for clarity later. R1 on top, closer to higher voltage, R2 on bottom, and R equivalent is just R1 plus R2 using the rule for adding resistors in series. From this, we can now use Ohm's law to determine the current. And because this is a simple series resistor circuit, the current in each element will be the same and will be the same as the current through the entire circuit. So we'll just say determine I for each component as well as each individual component as well as the whole circuit. So that will be done using Ohm's law. V equals IR. So I equals V over R. So 18 volts over our equivalent, which is 2.012 mega ohm. Simply adding 12 kilo ohm and 2 mega ohm. Now I need to grab my calculator. I'll be using the Octave online calculator for demonstration. (18 over 2.012 E 4 times 10 to the 6. And there is our answer. 8.9 times 10 to the minus 6. The units will be amperes because it's a volt over an ohm. Or it could more simply write that as 8.9 micro amperes. It makes sense it's a small current because a current is severely limited by the presence of this very large 2 mega ohm resistor. Next, we're going to calculate the voltage across each resistor. So V1, which is the voltage across the first resistor, is IR1. So that will be 8.9 microamps times 12 kilo ohms. And V2 will be IR2, 8.9 microamps times 2 mega ohms. And then a few other things I need to calculate are going to be the power in each component. And for power, for the whole circuit, it's I times V of the supply. So I'll label this V sub S here. So 8.9 microamps times 18 volts, and the power in the first resistor, I times V1. Of course, V1 is the same as IR1, so I'm just going to substitute that in and write I squared R1. Those are numbers I have readily in front of me. It's 8.9 microamps squared times 12 kilo ohm, and P2 is I V2, or I squared R2. .9 microamps squared times now the bottom resistor value of 2 mega ohms. It's time for the calculator. If you want to use this calculator yourself, octave-online.net. It uses the Octave interface, which is identical to the program MATLAB, and it's available free at this website. So first we'll do this calculation. Make sure we're clear about the order of operations. I'll use parentheses. So that's the current times 12 E3, and I get 0.1068. Round that to 0.11, keeping two significant figures, and unit is a volt because it's amp times a ohm, and then 8.9 E minus 6 times 2E6 for 2 mega ohms, 17.8 volts. Now notice that 17.8 plus 0.11 is very close to within rounding errors of two significant figures to 18 volts. So in other words, these two should sum to the voltage drop across the first resistor plus the voltage drop across the second resistor should equal the total voltage drop. Let's do the powers, and I'm going to show you one neat thing about MATLAB or Octave is we get tired of writing the current all the time, so I'll define I to equal 8.9 E minus 6. And now when I want to do the power, I just take 18 volts times I. That's 1.6 times 10 minus 4 amperes, or 0.16. I'm sorry. Go back a moment, that should be watts. Current times the voltage is a watt a unit of power, SI unit of power, or 0.16 milliwatts. Now we're going to do I squared R. So I still have I in my memory. So R was 12E3, 12 kilo ohms, times I squared. This is a very small number. .5 times 10 to the minus 7 watts, or 0.95 microwatts, and mega ohms times I squared. So 2E6 times I squared. .58 times 10 to the minus 4 watts, which is 0.15 milliwatt. 158 milliwatt. Why did I make that? And notice that the power in the second resistor plus the power in the first resistor have to add up to the same power dissipated by the entire circuit. So let's look at the questions. We have solved for the power, voltage, and current in each circuit element. We have solved for them in the entire circuit. And the resistor that identifies the most power is the second one. So this is the most power and this is the least power, and the reason is that the current through both resistors are the same, most power in resistor with largest voltage drop, which of course is the second one, or the higher resistance resistor. All right, let's just do a couple more. same question, but now we have two resistors in parallel, 1.2K and 322 ohm. Both are, of course, on the same supply, which is 6.2 volts to 0 volts. We begin the same way, making this into a single effective resistor. Equivalent resistor in this case is 1 over R1 plus 1 over R2, and take the inverse of that entire quantity. For clarity, we'll call this one R1, and the second one here farther out, the 322 ohm R2. Let's get some numbers in that. I'm going to use Octave again for this. There's command clear all, gets rid of all of my variables. So for instance, if I type I, it gives me a predefined value, whereas the one I defined before, I'm going to call R1 equal 1.2 E3 for 1.2 kiloohms. I'm going to call R2 322 ohms, and our equivalent I'll just calculate as 1 over R1 plus 1 over R2, and the entire quantity to the minus 1. And I get 253 ohms for this equivalent resistor value. $254 ohms. Let's talk about this value for a moment. Notice that this equivalent resistance is actually less than either R1 or R2. And so by adding extra resistors in series, we present more places for the current to flow, and therefore drop the total resistance. Again, think of the water analogy. If this seems confusing, we have a very large pipe here at the 322 ohms. Lots of current we expect to be flowing through this one, somewhat less current through R1, but the sum of them together is able to transmit more current than either one of them apart. So quite a different situation than resistors in series, and that's what this reciprocal rule that we used helps insist upon. Okay, so we have our equivalent. At this point, we proceed very similar to the previous problem. So we're going to figure out the current through the circuit, but now we have to figure out the current through R1 and the current through R2 separately. So I1 using V equals IR, or I equals V over R, will be 6.2 volts over R1 and the current through the second one, 6.2 volts over R2, or 6.2 volts over 322 ohms. All right, time for the calculator again. I'm going to define a V supply, or Vs, to equal 6.2. And so I1 is Vs over R1, and I2 is Vs over R2. And now I just have to write these numbers in. .17 times 10 to the minus 3, which is milliamps, and I2 is 0.0192, so I will call that 19.3 milliamps. And we'll see that if we add up these two currents, 5.17 plus 19.3, we'll have a total current in the circuit or 24.4 milliamps. Total current again is larger than any individual current because the current can go through either path. Okay. So we have the voltage already automatically. V across the circuit is the supply voltage, which is 6.2 volts, and that's equal to V1 and is also equal to V2. So it's going to be pretty straightforward. We have to multiply these numbers together to get the power dissipated. Let's start with the total power in the circuit. P is going to be the supply voltage times the total current, or 6.2 volts times 24.4 milliamp. And so the total power dissipated in the circuit is 0.151 watts. Or if you want, 151 milliwatt. P1 will be I1 squared R1, and P2 I2 squared R2. Notice that in this case the circuit's in parallel. There's a different current through each resistor, so that's why I have an I sub 1 and an I sub 2 for each of these. Again, it's IV, where V is equal to IR, or I squared R for the power is what I'm using. So doing the first one, P1 is R1 times I1 squared. And P2 is R2 times I2 squared. Alright, so for P1 I have 32 milliwatts. And for P2 I have 119 milliwatt. And I'll use my calculator here to show you that if I take P1 plus P2, I get 151 milliwatts. That's the same as I calculated by using the equivalent resistor and the total current of the circuit. So the power dissipated by the resistors individually equals the power dissipated by the equivalent resistor times the total current through the circuit, as it should. So that's good. Works out. So the one that dissipates the least power is clearly P2. So this is least. I'm sorry, that's most because it's 120. And the least power is P1 at 32 milliwatts. Why does P2 dissipate the most power? P2 dissipates the most power because it's the same voltage and a lower resistance, so more current flows through it. That is, more current at same voltage. Passes or flows through R2, so it consumes the most power. And that's my conceptual explanation of why that's the case. Now this problem I have given on homework. It is the same as the previous problem, and I'm going to help get you set up here. And the main tricky thing is that you're adding multiple resistors in series, and so when we turn this into an R equivalent, it's going to equal 1 over R1 plus 1 over R2 plus 1 over R3, and the reciprocal of that entire expression, and labeling to use R1, R2, and R3. So R1 would be 1.2K, R2 322K, and then R3 50 ohms. And I think you can even look at this and by inspection guess what the answer conceptually is, which resistor is going to draw the most current and therefore is going to sort of dominate the circuit, having most current flow through it and dissipate the most power. But this problem I leave you to work out on your own. All right. Another one of these problems, a little bit more complex. It's got 3 resistors, but they're not all in the same configuration. The current can flow from the 9-volt power supply one of 2 ways to eventually get back to a lower 3 mega ohm resistor. So this will be a little bit more of a complex problem that I'm going to run through with you. Label some resistors. R1, I'm going to call R2, the one next to it, and R3, the one at the bottom. And the first thing I'm going to do is turn this into a problem where I have looks like 2 resistors in series by making an equivalent resistor out of these top 2 over here, and then keeping the bottom one the same. So this will be a multiple step problem. So the same V supply of 9 volts, 0 volts, and R3 stays in place. At this point, the problem looks an awful lot like the first problem we did, but we'll go through it again here. We just are going to substitute in R1 plus R2. Excuse me. We're going to use the resistors in parallel law, because these two, 1R1 and R2, are in parallel. So it'll be 1 over 56K plus 1 over 220K, all to the minus 1 power. And I'm going to label this R equivalent 1, because we're going to have a second R equivalent where we combine these two in a moment. So let's get out the calculator. I'm going to clear everything and get some definitions in here. Make my life easier. R1 equals 56 E3 for 56K. R2 is 220 E3 or 220 kilo ohms. So I misspoke there. That should have been R2. Get rid of RW or whatever that is. And then R3 equals 3E6 or 3 mega ohms. There we go. Okay. So R1, R equivalent 1 is 1 over R1 plus 1 over R2 to the minus 1. And that's 4.46 times 10 to the 4, or 44.6 kilo ohms. That makes sense. That's a smaller value than either of these two resistors on their own. So the effective resistance is less than them on their own because each can carry current. So that's R equivalent 1. And then we're going to turn this whole thing furthermore into a single resistor, still from Vs to 0, which I'll call R equivalent 2, and that's going to be R equivalent 1 the top resistor plus R3. So R equivalent 2 is R equivalent 1 plus R3. And it ends up being just over 3 mega ohms, 3.04 mega ohms. And that also makes some sense. 44K plus 3 million is just a little bit over 3 million. And this number is larger, slightly larger than any of these resistors individually, since the current has to flow through more resistance. So let's look at this REQ2, which is the single resistor that represents this whole circuit. And let's figure out what is the power and voltage there. So the voltage across this is V sub S, so the current is easy to obtain. This is the current through the entire circuit, so I'll use no subscript there. The current through the entire circuit must be V sub S over R equivalent 2. And the total power in the entire circuit must be I times Vs, but that would be the same using V equals IR as I squared R. Don't have I yet. We could use, though, P equals IV, or I equals V over R, so that would be V sub S squared over R equivalent 2. And that I have the numbers for. So Vs over R equivalent 2 is 9 volts. R equivalent 2 is 3.04 mega ohm. And this would be similar, 9 volts squared over 3.04 mega ohm. Let's put Vs in the calculator. Sorry, I covered that up. Vs is 9 volts. So I is Vs over R equivalent 2, or 2.96 microamps. And the power is Vs squared over equivalent to, so that's 26.6 micro watts. Not much power is concerned, only a few microwatts. That's because of the very large current limiting resistor limits currents through the whole circuit, which keeps the power consumption quite a lot. It's quite a large current limit. At this point, we can proceed a bunch of different ways. One of them is probably to look just at R3. For R3, we know now the current. So for R3, what power? Should be P3 equals the current of the whole circuit, because it all has to go through that resistor, times R3, or I squared. Let's see how we want to do this. Let's go back a few steps. Use this form here, Vs squared over R equivalent. Except, no, we don't have the voltage yet. Yep, we'll need the voltage first. So V3 equals I R3. .87 volts. This makes sense because most of the voltage drop is across this large resistor. Whereas these two resistors combined are only 44 kilo ohms, so only a little bit of voltage drop is there. From this then we can figure out quite easily what is the voltage drop across R1 and R2. So V1 is going to be equal to V2. They're connected to the same voltage on each side. So that would be I times R equivalent 1. .13. And that's the same for V2. I can in octave just write V2 equals V1 and assign it that way. This is nice because 0.13 plus 8.87 equals 9 volts. That is the voltage drop across the first two resistors plus the voltage drop across the second equals the voltage drop top to bottom. So that makes sense. What else are we missing? I guess we can now do the power. In the third resistor, power in the third resistor is the current in the third resistor, which is the current in the entire circuit, squared times R3 So 26.2 microwatts. Notice how close this number is to the power dissipated in the entire circuit. So most of the power is going to end up being dissipated in R3. Now we go backwards to figure out the current in 1 and 2. So now go backwards, I1 and I2. V equals IR, so I equals V over R. So that was V1 over R1 and V2 over R2. Of course, V1 and V2 are the same as we have over here. And so the numbers are 2.36 microamps and 0.6 microamps. More current is running through I1 because I1 is 56K and is a smaller resistor than R2 at 220K. Now we can finally get the powers for the individual resistors. We already have P3, so after this step we'll be done. P1 be I1 squared R1 and P2 I2 squared R2 So P1 is 0.31 microwatts. And P2 is 0.08 microwatts. And compare that to P3 at 26.2 microwatts, or the total power dissipated in the circuit of 26.2 microwatts. And so the least is definitely the least power is R2, so this is the least power. Where's R3 is the most power. R1 lies somewhere in between. Why is this the case? The biggest voltage drop is across the biggest resistor. When the resistors are in series, that's 3 mega ohms. Then considering the resistors in parallel that remain, most of the current, and therefore most of the power, is going to be dissipated in R1, leaving the smallest amount of current and the least amount of power in R2. And that's our complex problem solving for all its currents and all the voltages. Well, here's something that looks like a real messy problem, but I am going to show you how it's set up. And get you started on it. We're going to start with making this an R1 equivalent and an R2 equivalent from the supply to 0, in R1, R2, R3, and R4. So those are expressions for these two equivalent circuits, and then we'll turn those into a single resistor R equivalent 3, which is just R equivalent 1 plus R equivalent 2. The current through the entire circuit will be ES over R equivalent 3 the power in the entire circuit will be this total current times the supply current and I will use the voltage divider equation to determine the voltage across R2 equivalent, which is the same as the voltage across R3 or R4 because they're connected here. So the voltage across 3, which is the same as the voltage across 4, we use the voltage divider equation, which says it's the bottom R2 equivalent over R1 equivalent plus R2 equivalent times the supply voltage. So that gives us V3 and V4. V1 is equal to V2 and has to be equal to the supply voltage minus, say, V3 or V4. So now I have the voltages across each resistor, I have the currents through the entire circuit, let's get the current through the individual resistors. So current through 1 is V1 over R1. The current through 2 is V2, which I have here, over R2. The current in resistor 3 is V3 over R3, and the current in resistor 4 is V4 over R4. Okay. And then we can just make a table of the powers. P is equal to I total, IVS, we already got that. So P1 is I1 V1, P2 I2 V2, P3 I3 V3, and P4 is equal to I4 V4. And that's everything, but I haven't put any numbers in. Why haven't I put any numbers in? Because I think I can just do it with the calculator at this point. Okay, I'm just going to type in all the quantities, throw in all the equations, and then just output all the results. First, R1, which is 56 kilo ohms. R2 is 220 kilo ohms. R3 is 3 mega ohms. And R4, which is 56 kilo ohms. R1 equivalent, or I'll call it R equivalent 1, is 1 over R1 plus 1 over R2, and then the inverse of that entire expression. Just parentheses, 1 over R1 plus 1 over R2, the inverse. Then for our equivalent 2, we replace with the 2 bottom resistors. Then for V3, let's do our equivalent 3 first. That's our equivalent 1 plus our equivalent 2. So I'm up here. Now V3 and V4. V3 is R equivalent 2 times Vs. No, I think we're going to do Vs. Let's do Vs of 9 volts. Vs is 9, sorry. There we go, that's up here. Now back to V3 and V4. V3 is R equivalent 2 times Vs divided by the quantity R equivalent 1 plus R equivalent 2. V4 equals V3. V1 equals Vs minus V3 here. V2 equals V1, again because they're connected at the top and bottom. Let's do the total I and the total power. I is Vs over R equivalent 3. Power equals I times Vs. And now we'll do the 4 currents. I1 equals V1 over R1. I2 equals V2 over R2. I3 equals V3 over R3. I4 equals V4 over R4. And then finally the 4 powers. P1 equals I1 times V1. P2 equals I2 times V2. P3 equals I3 times V3. Oh, did I miss I3? Yes, I missed I3. Made a mistake here. That should have been I3 equals IE. There we go. And now I can go back and do P3. P4 equals I4 times V4. And I have all the quantities in the problem.